My thanks to Dan Brown for inspiring the title to this video. Really, I should have titled it Agents, Demons and the Blackboard, but the joke wouldn't have worked. In artificial intelligence, agents and demons are essentially the same thing. They are small pieces of code that lie dormant until a certain set of conditions spur them into action. Then they carry out certain steps and change the state of the system under consideration before going back to sleep again, while other agents, or demons if you like, take over, triggered by the new set of conditions that exist. It was one of the pioneers of artificial intelligence in the 1950s, Oliver Selfridge, who first formulated the idea of agents working together on solving a problem. He coined the term demons for the components of his Pandemonium system, which he developed in order to recognize simple visual images, such as uppercase letters of the alphabet. Pandemonium was the first of several feature models which were developed as a response to the prevailing theory of how the human mind recognizes images. Before feature-based models, it was generally believed that the human brain somehow had a template for every common object, and we recognized what we saw by detecting to what extent it matched the archetype in our memories. It was believed that we all developed stereotypical images somehow programmed into the neurons of our brain, and when we saw an object, we subconsciously compared it with the countless possible stereotypes we'd learned, choosing the one with the greatest overlap. There's a fair description of the template concept, together with the problems that it suffers, in Human Information Processing by Lindsay and Norman. Link in the description. Take the concept of a dog, for instance. Dogs are the most varied species in the world, mainly due to selective human breeding, and yet we all recognise a dog when we see one. Admittedly, there are some dogs that look like nothing else on earth, but generally speaking, we know a dog by sight, regardless of its breed, which way it's facing, whether it has a coat or other accoutrements, and so on. Pandemonium attempted to address weaknesses in the template model of image recognition by concentrating on features rather than the whole. In the case of dogs, feature detectors will look for fur, size, body shape, head shape, and so on. If enough boxes on the dog feature list were ticked, the system will conclude that the object in question was a dog. The more experience the viewer had in recognizing dogs, the more features associated with dogs would be learned, and the easier this task would be. For instance, none of the dogs you see on the screen at the moment has fur, but you still recognize them as dogs. The feature detectors in Pandemonium were the demons. Selfridge envisioned them responding to each other and, as he put it, yelling. The louder any demon yells, the more demons down the line take notice of it. The example here shows Pandemonium trying to recognize an image of a printed letter R. The image demon loads the image into the system. Then feature demons take a look at it. Each feature demon recognizes one particular aspect of the image. In the case of alphabetic letters, these aspects are things like short vertical lines, diagonal lines rising to the right or to the left, and so on. Letter segments, in other words. In this case, the demons that yell are the ones that detect vertical lines, short diagonal lines rising to the left, for the tail of the R, and a semicircle extending to the right. The other demons stay silent. The letter demons then listen to the feature demons. Some, like the demon for O, respond to the detected semicircle. Others make more noise, such as the demons for P and B, as they respond to more than one feature. The final demon is the decision demon that detects which letter demon is yelling the loudest, the letter R in this case, and makes its decision based on that. Viewers familiar with neural networks will probably have noticed the similarity between this structure and a feed-forward neural net, and indeed Oliver Selfridge carried out some early work on neural networks. However, the concept was soon broadened into the Agents and Blackboard structure. Unlike Pandemonium, in which demons always responded in a predictable manner to those in the layer above them, the agents did not pay attention to other agents, but to a common knowledge source, the blackboard. The blackboard stores the current state of the problem to be solved, initially in the form of a goal to be achieved. This is joined by things like facts known, constraints, sub-goals and the like. The agents continually pay attention to the blackboard. They can be triggered by the information stored in it, or by some subset of the information, in which case they carry out their function, whatever that is, and then add the results to the blackboard, or rewrite what's on there already. This repeats until either a solution to the problem is found, or the current state of the blackboard doesn't trigger any agents, i.e. the problem has reached some sort of stalemate. That, of course, might mean that no solution is possible. One extra component that we might need in such a system is an agent that controls access to the blackboard. Extending the blackboard analogy, if all the children are allowed to write on the thing, we might need a teacher to sort out disputes. If all the agents respond to different triggers, there's no conflict. You never get two wanting to write on the blackboard at the same time. However, you might get more than one agent that responds to identical blackboard configurations, and they might not produce exactly the same results. In this case, the control agent will decide which one takes priority. The problem becomes worse when agents are competing to solve different goals. For instance, the problem to be solved might involve planning the route for a new road system between a series of towns, where the different agents represent the varied intentions of the interested parties. One agent might be trying to reduce the total length of road built so as to minimise expense to taxpayers or environmental damage done, while another one, representing local motorists, might want to increase it to reduce journey times. In situations like that, it will be up to the teacher to orchestrate some sort of compromise between the warring agents to ensure that some sort of solution was possible. Various attempts have been made to introduce some standards into the Agents and Blackboard model. One of these, for instance, was the Learnable Task Modelling Language, or LTML, used to store data about objects, both physical and theoretical, in the system and relations between them. Essentially, it allowed knowledge to be stored in a form that was readable by both the machine agents in the system and by the human beings monitoring it. Since the language stores details of both objects and control structures, such as if statements, it is very close to being a proper computer programming language in itself. In the pre-neural network days, Agent and Blackboard type systems achieved some notable successes. For instance, the Pandemonium system was used to recognize printed letters on envelopes and to translate Morse code into English. Two famous programs that used an adaptation of the blackboard were the Hearsay 2 speech understanding system, developed at Carnegie Mellon University, and the Copycat system by Douglas Hofstadter and his team at Indiana University, which solved the sort of analogy problems that you find in intelligence tests. However, since the advent of neural networks and their pattern matching abilities, this sort of approach has generally fallen out of favour, although I dare say you could still find it used in some recent AI applications if you looked hard enough. So there you are. The Agents and Blackboard method works well for any problem that naturally breaks down into parts that influence or communicate with each other, and as such forms a useful tool in symbolic AI. The example JavaScript program for this week shows how it can be applied to solving Sudoku puzzles, in which every row, column, and 3x3 cell block is controlled by its own agent. I aim to put out a video on a different artificial intelligence topic every week, so please do consider subscribing to the channel if you think that sort of thing would interest you. Also, if you like this video, please click on the like button below, and if you didn't like it, why not leave a comment explaining why? Thank you.